Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RET 120 Hydraulics. This lecture is entitled Troubleshooting Electrically Controlled Hydraulic Systems and another example of electrically controlled hydraulic systems. Okay, so I'm definitely asking you to re-familiarize yourself with the previous lecture entitled Electrical Controlled Hydraulic Systems, because we're picking up where that one left off. Okay, so following that lecture, you guys might be dividing yourselves into two camps. Number one, whoa, I need to overlook this thing again because it's something new to you. Don't worry, revisit that lecture, you'll have no problem. Sometimes it takes a little bit getting used to this here. We're going to revisit the same circuit again. And the second camp of you guys are like, this is so cool. Electrically controlled hydraulic systems can never go wrong. And I'm here to tell you they do go wrong, and they go wrong in a big way, and you need to learn how to troubleshoot them. Okay, so here is our same electrically controlled hydraulic system we've discussed in our previous lectures, where it is a clamp and press hydraulically sequenced electrically controlled hydraulic system. Okay, let's just go ahead and press push button 1. Push button 1, we press it. It's closed. It's normally open. It closes. What happens to CR1? Energizes. CR1A closes. CR1B closes. CR1C opens. Here's where the troubleshooting comes in. Normally, we would expect a path of current from here to there. What happens if LS1, which is right in that first rung there, it was supposed to be normally closed, but what would happen if it was open? Okay? Well, quite obviously, CR1 would have never energized. Okay? So right from the bat right there, you would expect a major problem if LS1 was already open. So it helps to figure out, what is the circuit supposed to do? And again, that is the ultimate troubleshooting advice to give you for any situation. What is it supposed to do anyways? If you don't know what it's supposed to do and you're trying to troubleshoot it, you might be troubleshooting a normal feature of this circuit. Okay, so let's go back to our troubleshooting example. Let's pretend LS1, it's open, it's supposed to be normally closed. I press push button 1, I can press it all day long. There is no path from here to there. Okay, so CR1 doesn't even energize. I would check these wires in between push button 1 and limit switch 1. This wire here, does my relay have a ground? I would check limit switch 1, which is the troubleshooting example I gave you, and I would actually check the relay itself. You know, the relay itself might be burned out. Okay, so that's our first troubleshooting example. But let's go ahead and put ourselves back into limit switch 1. It's normally closed, it's functional, our relay is functional, and we press push button 1 again. Okay, so boom, got a path of current, lights up, this guy closes, this guy closes, this guy opens. Okay, so what happens? Solenoid A energized, we switch to a straight through condition, and our clamper tries to extend because that pressurized flow enters here. It can't because of the sequence valve until pressure in the clamper comes to our required pressure. Let's say it's 500 psi, and our clamp jams. It's kinked sideways. Pressure builds up, builds up, builds up. Our sequence valves open, and the presser extends without it being clamped. There's a problem. Okay? So obviously this is a hydraulic problem with this thing. Troubleshooting is not in the electrical circuit. It's in the hydraulic circuit. Okay, so what is this presser making a decision on? It is only making a decision on pressure because of the hydraulic sequence valve. So if I was to modify this circuit, what I would probably do is have some pressure sensing, and maybe the addition of maybe other limit switches here on our clamper to see, hey, as my clamper, I know it's reached pressure, but it has even hit this limit switch down here. So basically I'm checking for pressure and position. Okay, so our first example was a problem within the electrically controlled circuit. Now here's a problem in the hydraulic circuit itself. Okay, so I'm going to redraw this here. Okay, let's say our clamper's not jammed now. We're still in our straight through position. Our clamper has extended. It's gotten a hold of the workpiece. Pressure starts to rise, and the sequence valve opens. Our pressurized flow, enters our cap end of the presser, and this thing starts extending. Notice limit switch 2. Limit switch 2 is normally closed, being held open. And let's say it's stuck. Let's say there's some resin or some dirt or something like that stuck inside limit switch 2, where it's normally closed, being held open, and it stays open. Okay? So limit switch 1, this thing extends, clicks this guy, limit switch 1 right there, that guy opens up, de-energizing CR1, changes everybody back to our to our end state there. And what happens now? Well, because that thing's open, solenoid B does not energize and it does not retract. Okay, so again, here's a problem that our electrically controlled hydraulically sequenced circuit, it's not seeing that it's completed the press. Okay, one could easily do, let's just start off from the beginning here. So I've cleaned up our diagram here, and again we're starting off from the get-go. Switch 1 is normally closed. Okay, so we press our push button 1. CR1 energizes, changes the states of its associated contacts. Solenoid A energizes, bringing us to our straight-through condition. Pressurized flow enters our clamper. It extends until pressure, and again, it's not getting jammed this time. Extends until the pressure and the sequence valve is overcome. Our presser extends, and this time limit switch 2 is not being held open by some foreign object. It closes as this guy extends. Let's say limit switch 1, it's got a functional switch, but our rocker arm is broken off. It's on the floor. It's a still functional switch, but what happens is our press cylinder just bypasses it, and it's waiting and waiting and waiting. So it's almost the same circumstances we had last time, where it was not, it's extended, the presser is extended, both clamp and press are extended, and it's not retracting. But this time, our CR1 is still energized, and that pressurized flow is entering our presser and our clamper. So similar circumstance, different troubleshooting. So these are the things you need to start figuring out when you're walk on to a troubleshooting situation. Where is the status currently of the system? What's the status of the ladder logic and the hydraulic system? And let's say you've gotten to this place, you walk up to it, and you're like, oh hey, check it out. There is the broken rocker arm for our limit switch. You go ahead and replace that thing. It trips, pops this guy open. What happens? Relay de-energized. Everybody goes back to its states here. And now what happens? Solenoid B is energized, switching us to our retract condition. By the way, that's off, so solenoid B is the only one on because you don't want them fighting each other. And what happens? Well, pressurized flow enters the rod end of each of these guys. Because we're in our cross through, and because of our bypass here, these guys retract simultaneously. Okay, bringing us back to the point where limit switch 2, as this thing was retracted, hits this guy again, reopens that, de-energizing solenoid B, and we're good to go. Okay, because limit switch 1, by the way, has closed again once that thing retracts. We're right back at the beginning where we started. Okay, so notice how the press and the clamp simultaneously retracted. Okay, because our next example, which we're about to do, is going to have some added functionality. Notice we had our jammed clamp problem there. It was making the decision strictly off pressure. So let's make a circuit now electrically controlled, electrically sequenced, where it's checking the pressure and position of our clamper. So not only is it making sure that it's got sufficient strength, it's actually making sure it's there. Okay, the other thing too is notice how our clamper extended, then our presser, and then they simultaneously retracted. Well, check this out. Let's do this. Let's clamp it, press it, retract the presser, then retract the clamper. Okay, so let's say it's a device, or excuse me, a piece of work that needs to be precisely drilled. You don't want it moving while that presser is retracting. So let's go ahead, and I'm going to go ahead and switch to another page here where there's a new circuit. Okay, so here's our second circuit. Now again, urge you to fight that immediate impulse to jump out the window and panic. Again, don't panic. Identify what you know. Let's start off with our hydraulic circuit. Obviously a pump, pressure relief valve. Here we've got a directional control valve 1. Looks to have 2 solenoids on it. Additionally, it's a tandem center. So if I put a pressure gauge right here, I would expect an incredibly low pressure, okay, because it's returning to tank at low pressure. Got our clamper with our limit switches 1 and 2. Okay, so now notice, in addition to previously where it was just making a decision off pressure, we've got position sensors on our clamper now. Okay, where's the pressure decision being made? Probably right here, pressure switch 1. Okay, so again, we're going to, as we see in the ladder logic a little bit later, we're going to make a decision off pressure and positioning for our clamper. Okay, what is going on right here? It looks like we've got a second directional control valve. This kind of makes sense here, because what we're going to do is a clamp and press. One would never expect, basically you need to have the thing clamped and then pressing it. So basically this directional control valve 2, solenoid A, because it's only in 2 position, it's only got 1 solenoid, it's kind of acting like a sequence valve, maybe making decisions off of this pressure switch and these limit switches here. Okay, so we'll see how that works inside our ladder logic. Here we've got our presser. What does it have on it? Sensing it? Proximity sensors. Proximity sensors, if you remember, are very similar to limit switches, but they're not detecting the physical presence of an object. They're detecting basically a magnetic object entering its field of influence. Okay, so look at proximity sensor 2. Notice how it's close to the piston. I would expect in the ladder logic that proximity sensor 2 is probably a normally closed being held open, a normally open being held closed, because it looks like it's already in that retracted situation. Same thing with limit switch 2 here. Again, it's making contact with the clamp rod end. I would suspect in our ladder logic that I would see something akin to a normally open being held closed or normally closed being held open. We'll see if we're correct. Okay, let's go see if we're correct. Here's the ladder logic. Where's the ladder logic? Right there. This big thing right here. Okay, so let's look at this thing. What is this right here? Well, it's a mechanical interlock. A mechanical interlock on limit switch 2. So that means there are 2 switches that whenever it's activated, 2 switches change their states. Let's make it even more confusing. It's got some arrows indicating it's being held in its position. Like I said before, limit switch 2 right there is being held in some position. So it looks like our top rung here is a normally open being held closed, and here's a normally closed being held open. At any time that clamper extends, this guy is going to open back up, and this guy is going to close. Okay? Push button 1, what is that? That's a normally open switch. Proximity sensor 1, that's a normally closed proximity sensor. It's located right there. CR1A, who controls CR1A? Well, probably CR1. It's a normally open contact. When CR1 energizes, we would expect that to close. Here's a neat feature right here, a normally open pressure switch in series with a normally open limit switch 1. Check it out. It needs to have pressure, and it needs to be in the correct position to energize directional control valve 2 solenoid A, which is this guy, extending our pressor. So this makes sense. This is where you've got some added functionality. It's checking pressure and positioning within this rung before it extends directional control valve 2 solenoid A. Okay? So, by the way, what's this guy here, CR1A, in parallel with the push button? It's a holding contact, meaning I can let go of push button 1. I press it once, CR1 energizes, it changes the states of the CR1A's contacts and closes, meaning I can let go of push button 1. Okay, second rung, we've already talked about the mechanical interlock on limit switch 2. What's this guy? That is CR2A. It's normally closed. Where's CR2? Right here. Anytime CR2 is energized, CR2A will open. And that's in series with directional control valve 1 solenoid B. Where is that? Up there. Okay? Now the third leg, looks like we've got CR1B, which is a normally open contact, which will close when CR1 is energized. We've got something in parallel with it. Proximity sensor 2. If you remember right, proximity sensor 2 is something in its de-energized state right there. It's being held back or being activated, whatever it might be. Okay, so it looks like in this particular case it's normally closed, and because of this arrow it's being held open. Okay? We already talked about CR2 in this rung, in parallel with directional control valve 1 solenoid B. Where is that? Right there. I may have made a mistake here. I did. One moment. That should actually be solenoid A. Looks like I rewrote over it. So make that change on your diagrams. So directional control valve 1 solenoid A is in parallel with CR2. Okay, let's go ahead and clean this thing up here, and we'll go ahead and see how this guy runs. Okay, so I've gone ahead and cleaned up our hydraulics and our ladder logic schematics. Before we go into this, you may, now that I've made the changes here, again, remember I made that change, I would recommend, and this is how I like to learn these ladder logics and hydraulics, make a copy of the schematic, make a copy of the ladder logic, and just in pencil, you know, kind of how I'm doing with the different colors here, show how the switches open up and close. That way you can figure out, okay, where am I in this sequence of everything? Okay. Once you get to a point where it recloses or reopens, whatever, you just erase that pencil mark. You know, again, you could use it in different colors. Alright, so here is how we're going to do this. Push button 1 is closed. There's a path of current from positive to negative because limit switch 2 at the top is normally open being held closed, and again we're retracted right there. So there is a path. CR1 energizes and its associated contacts change states. Meaning this guy, does this guy change right here, CR2A? No, it doesn't, because that's controlled by the CR2 relay. CR1B closes. I can let go of push button 1 because of the holding contact provided by CR1A. Let's look at what happens on the third rung. Because CR1B energized, CR2 energizes. This is a really neat feature here because another relay excited another relay. So it's a sequential operation here. Alright, CR2 has energized. Its contacts are going to go ahead and change states. CR2A should open. Look at what's in parallel with CR2. Directional control valve 1, solenoid A. So that should energize. What happens when directional control valve 1, solenoid A is energized? Right there, we move to our straight through condition. What happens? Our clamper goes ahead and pressurized flow enters the cap end and it starts extending. Does our presser extend? No, because directional control valve 2 is in our cross-through connection. It's continually retracting the presser. Okay? So once the clamper starts to extend, it leaves limit switch 2 behind. So what happens? That via the mechanical interlock here, I'm just going to draw this in red. It's a normally open being held closed. This guy opens up. This is a normally closed being held open. It closes right there, and our circuit has changed once again until, now it's continually extending. It's not really going to change until it hits limit switch 1. So now it hits limit switch 1. Limit switch 1 closes. And let's go back to our troubleshooting example. What would happen if limit switch 1 was broken off? Well, it wouldn't close and would not enable that particular leg of this ladder logic. Okay, now basically it's going to sit here. Its reach positioning is sufficient pressure available for the clamper. Not yet, but it's rising and rising and rising. And let's say this thing's set for 500 psi. At 500 psi, what happens to our pressure switch? It closes. Here's where the magic happens. Because of the holding context, CR1A, through our normally closed proximity sensor 1, we have a path of current enabled by our pressure and our positioning. So some added functionalities. Yes, there's some additional electrical components to directional control valves in this particular case, but we are checking for pressure and positioning now. What happens to directional control valve 2, solenoid A? It energizes, and now our presser extends. What happens to our presser once it extends? Well, because proximity sensor 2 is, down here in our ladder logic, is normally closed being held open, it's going to close until we hit proximity sensor 1, at which point that opens up. Now there's a major state change here because there is no longer a path, because the push button 1 is open again, and via the holding contact we were capable of maintaining energy on the CR1 relay, but we just broke it right there. So what happens now? CR1 de-energizes. This guy opens. This guy opens. This guy turns off. So directional control valve 2, solenoid A comes off. And our presser should retract. Okay, so this is pretty neat. We've clamped it. We've pressed it. Now the presser is going to retract. What happens when the presser retracts? Proximity switch 1, because it's left this region, recloses until it retracts all the way to proximity switch 2, which, if we remember right, was normally closed being held open. So it goes back to our being held open state. Again, just think about the troubleshooting opportunities here. There's no limit of things that can possibly go wrong. Okay, it's opened up again. Let's say it just didn't open up again. It would constantly stay closed. There's your problem right there. Because what happens is, via this relay here, CR1B, we've broken that path and this path. What's going to happen to CR2? Well, it should de-energize, turning off directional control valve 1 solenoid A and reclosing that guy. Okay? So, directional control valve 1 solenoid A is turned off, and because this limit switch 2 right here is a normally closed being held open, it's not in that position anymore because it's extended all the way to limit switch 1. We do have a path of current here to energize directional control valve 1 solenoid B to retract it. Okay, so we've already retracted our presser. Let's retract our clamper. Retract our clamper. Limit switch 1 reopens because it's retracting. Oh, by the way, the pressure has dropped because it's just super limited load, pretend, until it hits limit switch 2 again. It retracts all the way back to limit switch 2. What's it do? Well, this normally open being held closed comes back. What happens here? It's a normally closed being held open, breaking the path from here to there. And what happens? Directional control valve 1 solenoid B is turned off, and we're right back where we started. Okay? This is a complicated system. I know some of you guys are freaking out right now. Don't worry. What I'm trying to show you guys is just additional examples of how you, with some added components, you've got some added functionality, and just giving you a little bit more practice with holding contacts, mechanical interlocks, and some of the normally closed, normally open switches, and normally open being held closed, normally closed being held open switches, and some of the control logic you can possibly come up with here. I'm not expecting you to design anything like this right now, but I should expect you to be able to identify components within it, and given a basic ladder logic schematic, figure out what it's going to do. And additionally, be prepared for those events where it doesn't work like it's planned. Figure out where it is within a particular section of the ladder logic rungs, or maybe it's a hydraulic problem where a limit switch is not being tripped, or perhaps a cylinder is jammed, falsely tripping a pressure switch. Again, there's no limit of things that possibly could go wrong, but what you need to do is just figure out which functional areas are working, which relays, say, perhaps are energized, which switches are closed, and you should be able to figure out in circumstances where you are and what corrective action needs to be performed to get the situation resolved and this circuit functioning like it should be. Okay, that's it for troubleshooting of electrically controlled hydraulic systems, and this is another example of an electrically controlled, electrically sequenced, this time, hydraulic system. We're going to do this in a lab, and I've actually got some videos of this particular circuit built right here. So when you see these videos, what I'm going to ask you to do is use a copy of the ladder logic and the hydraulic circuit to see what I'm talking about when you look at the videos.